Welcome back to the session. Till now, we have seen what is LPP, what does uh, what is the importance of LPP, and we have also seen how to formulate an LPP. Given a real life scenario, how to write it in form of an LPP problem that we have seen till now. Now we are moving on to the solution domain, that is solving an LPP, solving a linear programming problem. There are two methods of solving a linear programming problem. One is the graphical method, other one is simplex method. Initially, we will be looking into graphical method of solving LPP. So graphical solution of LPP models. Here, graphical solution method can be applied only when there are two decision variables. This I told you earlier as well. Once again, I'm repeating. Graphical method can be applied only when we have two decision variables. More than two decision variables, your graph sheet will not support because your graph sheet is only two-dimensional. Therefore, if you have two variables, you can solve 2D. Right? So therefore, graphical solution procedure can be applied only when we have two decision variables. It can be used with three variables, but only with very great difficulty. If at all I am implementing this graphical solution on a computer and I am making use of the z axis as well, if at all I am defining or I am able to define a graph plane both all in x, y, and z axis, then you will be able to solve three-dimensional or LPP with three decision variables. But for our scope, we will assume that only problems with two decision variables can be solved using graphical method. Why do we use graphical method? Graphical method provides a very good visualization of how a solution for a linear programming problem is obtained. Visually, you will get to know the solution or the solution process of an LPP. Therefore, we learn graphical solution method. Whenever we are solving graphical method, there are two important terms. It is very much important for us to know. One is called the extreme points, the other one is called the optimal solution. What are extreme points? The corners or vertices of a feasible region is called extreme points. Anyhow, when we are solving the problems, you will get to know what are extreme points much more clearly. But for us, for time being, for us to understand, let us assume that whenever you are solving a problem using graphical method, you will get a region where the constraints are getting satisfied. That region, that closed region or an open region, many a times it will be either a quadrilateral or a pentagon. That uh, region is called feasible region, and the end points or the corners or the vertices of those uh, of that particular feasible region, I call it as extreme point. Then what is an optimal solution? This we have seen already in the earlier explanations. Out of many feasible solutions, only one solution will be the best possible answer, which will optimize the objective function. That is, either it gives the maximum possible value in case of maximization problem, minimum possible value in minimization problem. That is called the optimized solution, or it is the optimal solution. An optimal solution of an LP problem can be found at an extreme point of the feasible region. This is one basic assumption that we go through with in graphical method, that whenever you get a feasible region, we need not check all the points within the feasible region. If at all you check only the extreme points of the feasible region, then the optimal solution will lie on any one of the extreme points, right? When looking at the optimal solution, you need not have to evaluate all the points in the feasible region. Then what are we supposed to do? You have to consider only the extreme points of the feasible region. First, find the constraint in intersections. That is, identify the feasible region. After that, identify all the extreme points of the feasible region. Start at first extreme point, substitute that extreme point in the objective function, then go to the next extreme point, substitute it in the objective function, then go to the next extreme point, substitute it in the z equation. This process goes on. Once all the extreme points have been substituted in z and the z value has been evaluated, find that corner point x1 comma x2 for which the best z value is available. In case of maximization problem, maximum z value has to be picked. In case of minimization problem, minimum z value has to be picked. That will give us the optimal solution. Hope you have understood the process. Now, as we know, in LPP, there are two classes of problems. One is maximization problem, other one is minimization problem. For today's session, we will be considering only maximization problem or maximization LPP. To understand the procedure of solving LPP maximization type using graphical method, we will consider a problem and solve it. During the solution procedure, you will understand how to solve an LPP maximization type in graphical method. Before I move on to the problem, one thing I would like to tell you people here is, for the first time, you have downloaded the video, listen to it, and I expect you people to listen it for the second time. And along with listening, I want you people to solve the same problem that I've given now. Whatever problem I'll be discussing now, I want you people to solve the same problem along with listening to whatever I am saying. Fine? Accepted? Shall we move on to the problem? So the problem that I consider is max z is equal to 2x1 plus 3x2 subject to the constraints 2x1 plus x2 less than equal to 12, x1 plus 3x2 less than equal to 15, and the non-negativity constraint x1 comma x2 greater than equal to 0. This is the given problem. So once this problem is given, what are we supposed to do? So once the problem is given, we have written down the problem. Now what we are supposed to do is, to solve the problem, the first step is we are supposed to assume the constraints as equations. Here in the problem, the constraint given to us are inequalities of type less than equal to. So for time being, I will forget that it is less than equal to type and I will consider it as an equation. So consider the first constraint as an equation. What is the first constraint? 2x1 plus x2 less than equal to 12. This less than equal to, I will make it equal to and write it. So 2x1 plus x2 is equal to 12. So in this equation, for the first time, I will put x1 is equal to 0. I will put x1 is equal to 0. What happens? 2 into 0 plus x2 is equal to 12. Right? 2 into 0 plus x2 is equal to 12. So 2 into 0 is 0. We can skip that. What am I left out with? It will be x2 is equal to 12. So when I considered x1 is equal to 0, x2 value will be 12. So I will write these two values in form of a coordinate. So as a coordinate x1 comma x2, I will copy it down. So x1 is 0, x2 is 12. So the point is 0 comma 12. Next, for the same equation, I will put x2 is equal to 0. Let x2 is equal to 0. If at all I put x2 is equal to 0, what happens? 2x1 plus 0 is equal to 12. So in that case, x1 is equal to 12 by 2. So x1 is equal to 6. So when I considered x2 is 0, x1 becomes 6. So if at all I write it in form of a coordinates, x1 comma x2, it will be 6 comma 0. x1 is equal to 6 and x2 is equal to 0. So it will be 6 comma 0. So for the first constraint, I have got the 2 points to be 0 comma 12 and 6 comma 0. Okay. Now consider the second constraint. Going on to the second constraint is x1 plus 3x2 less than equal to 15. So this less than equal to, I should make it equal to, right? Consider second constraint as equation. It becomes x1 plus 3x2 is equal to 15. So same procedure, let x1 is equal to 0. When I put x1 is equal to 0 in the equation, 0 plus 3x2 is equal to 15. x2 is equal to 15 by 3. So what happens to x2? x2 will be 5. So the coordinate will be 0, comma 5. Okay. The coordinate will be 0, comma 5. Now substitute x2 as 0 in the equation. So let x2 is equal to 0. What happens to the equation? x1 plus 3 into 0 is equal to 15. x1 plus 3 into 0 is equal to 15. 3 into 0 is 0. You can just skip this term. You will remain with x1 is equal to 15. So when you write it as coordinate, x1 comma x2, 15 comma 0. So we have got 2 points for the second constraint as well. The points for the second constraint are 0 comma 5 and 15 comma 0. Hope till now the concept is clear. So we have got 4 points, 2 points for the first constraint, 2 points for the second constraint. Now let us see what to do next. Take a graph sheet and mark the axis. How do you mark the axis? It will be marked in such a way that your first quadrant is wide open. Your second quadrant I don't need, third quadrant I don't need, fourth quadrant I don't need. Why I don't need? Because of the non-negativity constraint. Non-negativity constraint says x1 is greater than equal to 0 and x2 is also greater than equal to 0. That means to say x1 is also positive, x2 is also positive. When both x1 and x2 are positive, it will be only in the first quadrant. So I am marking the axis in such a way that I get the first quadrant. I take the x-axis as x1, y-axis as x2. So I've made markings 0, 1, 2, 3, 4, 5, 6, 7, 8 up to 15 along x1, 0, 1, 2, 3, 4, 5 up to 16 along x2. Clear? Just taking a graph sheet, putting x-axis and y-axis and making the markings. I think there is no doubt here. Move on to the next step. Consider the first equation. The first equation points that we had got was 0, 12 and 6, 0. So plot this 0, 12 and 6, 0 on the graph sheet. 0, 12, 0 along x1, 12 along x2. So this is the first point. Next point is 6, 0. 6 along x1 and 0 along x2. So this will be the point. So I've got 2 points. So when I've got 2 points, I will join these 2 points with a straight line. Fine. So I got a straight line by the points. But the constraint was actually, what was the constraint? 2x1 plus x2 less than equal to 12. So when I considered it as an equation, I got the points as 0, 12 and 6, 0. But the actual constraint was less than equal to the given value. So when I say less than equal to, it is a region below the line. So the region below the line, I shade it. This will be my feasible region for first constraint. Feasible region for first constraint. Next, similarly, I take the second equation. The points for the second equation are 0, 5 and 15, 0. 0 along x1, 5 along x2. This is the point. Then the second point is 15 along x1 and 0 along x2. This. So these 2 points I join with a straight line, and this is also less than equal to type. Therefore, shade the region below the line. So whatever I have shaded in blue is the feasible region for the second constraint. The pink region is feasible region for first constraint. Blue region is feasible region for second constraint. But when I'm solving the problem, both the constraints have to be considered. Both the constraint should be true. Therefore, I will be interested in this region where both the shadings are present. Both pink and blue are there. That is the overall feasible region of the problem. So let me highlight it. So I highlight this particular region where both shadings I had. So I have highlighted it in orange. So now we have got a feasible region for the problem. Once we have got the feasible region for the problem, the corners of the feasible region, are called extreme points. So I am supposed to mark the extreme points. Always origin will be marked as O. So O, then this end point, I will mark it as A. This point of intersection is also a corner. So I will mark it as B. And this point, I will mark it as C. So how many extreme points we have got? 4 extreme points. O, A, B and C. What is the coordinates of O? 0, 0. What is the coordinates of A? It is 0, 5. What is the coordinates of B? So from the graph, I get it to be 4.2, 4.2, comma 3.6. So 4.2, 3.6. What are the coordinates of C? It is 6, 0. So I have noted the coordinates of the extreme points. After noting down the coordinates of the extreme points, now I am supposed to optimize or find out the optimal solution. So the step to do that is I am supposed to make a note of the points. O is 0, 0, A 0, 5, B 4.2, 3.6, C is 6, 0. Now consider the objective function given in the problem. Till now we were looking at only the constraints. Objective function we did not see. What is the objective function? Z is equal to 2x1 plus 3x2. 2x1 plus 3x2. That will be considered here. So 2x1 value in this point is 0. 2 into 0 plus 3 into x2. x2 value is 0. 2 into 0 plus 3 into 0. What will be the value? 2 into 0 is 0. 3 into 0 is 0. 0 plus 0 is 0. Now coming to point A. x1 is 0. x2 is 5. So 2 into 0 plus 3 into 5. 2 into 0 is 0. 3 into 5 is 15. So 0 plus 15 is 15. Clear? Next, coming to the point B. 4.2 is x1. 3.6 is x2. So 2 into 4.2 plus 3 into 3.6. Fine. So you get 2 into 4.2, which will be 8.4, and 3.6 into 3 will be 10.8. So 10.8 plus 8.4 will give you 19.2. Fine. The value will be 19.2. Consider the last point C. 6, 0. x1 is equal to 6. x2 is equal to 0. So 2 into 6 plus 3 into 0. 2 into 6 is 12. 3 into 0 is 0. 12 plus 0 is 12. So after finding out the value for all the extreme points, identify the maximum value. Why maximum? Because the problem was maximization type. Because they have asked us to optimize or maximize the objective function, I am supposed to take the maximum value, right? Highlight that particular row. So Z maximum value is 19.2 at x1 is equal to 4.2 and x2 is equal to 3.6. This is the final answer. So the optimal solution for the linear programming problem that we considered was 19.2 was the optimal solution at the point with coordinate x1 is equal to 4.2 and x2 is equal to 3.6. Hope the concept is clear. Now, one more problem for you to try. You try it out. Maximization problem. Z is equal to 40x1 plus 50x2 subject to x1 plus 2x2 less than equal to 40, 4x1 plus 3x2 less than equal to 120, and we have the non-negativity constraint x1 comma x2 is greater than equal to 0. Clear? Hope the concept and the explanation is clear. I want you people to try out this problem and kindly post your answers for this solution, for this problem. I want the Z max value, x1 value and x2 value. I want each one of you to send the answer for this problem in the comment section of this particular post. Hope you have understood. Once again, I am repeating. I want the solution Z max, X1 and X2 for this problem in the comment section of my post. Okay. Thank you. Have a nice day. Enjoy. Stay home. Stay safe. Don't go out anywhere. Keep yourself safe. Thank you.